If you solve this mathematical problem, you will get $1 million. We like to imagine science as exact, that somewhere behind modern technology there are perfect equations with perfect answers. But you're probably going to be surprised to know that we do not actually solve most equations exactly. In fact, some of the most important mathematical problems in physics are still unsolved today, and there is literally a $1 million prize waiting for anyone who can solve them. And yet somewhere, airplanes still fly, and weather forecasts still work, and rockets still launch, and modern civilization keeps moving forward. Because instead of solving reality perfectly, we learned how to approximate it. To explain this, we began with something simple, a one-dimensional metal rod, simple to us to understand intuitively. Suppose we initially heat the rod in the shape of a sine wave, and then we simply leave it alone while keeping the ends fixed at 0 temperature. Intuitively, we expect the heat to slowly dissipate over time. The hotter regions cool down, the colder regions warm up, and eventually the entire rod moves toward equilibrium. You can see here as a stacked 2D plot changing with time, or even better, as a 3D plot of heat. As this is the initial condition of heat, and it is slowly collapsing as it diffuses away. To capture that behavior, our question is, how do we describe it mathematically? Let us focus on a single point in the rod and plot the heat in that point. If that point is hotter than the neighboring points around it, the heat flows outward and the point cools down. But if the neighboring points are hotter, heat flows inward and the point heats up. So, the temperature at the point depends on how different it is from the surrounding region. Mathematically, this idea is captured using the second derivative with respect to precision. If the curvature is negative, meaning the point is hotter than its surrounding, the temperature decreases over time. If the curvature is positive, meaning the point is colder than its surrounding, the temperature increases. So now we can say this: the change of temperature over time is related to the spatial curvature of temperature throughout the rod, and this naturally leads us to the heat equation. This equation describes diffusion, the spread of energy through space over time. By the way, this explanation is more satisfying to me than mathematical derivation, because I'm an engineer, and it feels like it emerges directly from physical intuition. Of course, mathematicians derive this equation more rigorously using conservation laws and infinitesimal analysis, but we will not go through that derivation here. There are other videos on YouTube you can watch. Now that we have an equation describing the behavior of the system, we want something even harder, the exact solution. We want to predict the temperature at every point in every moment in time. One way of doing this is through a method called separation of variables. The idea is intuitive. We assume that the solution can be separated into one function that depends only on position and the other that depends only on time. So, if the initial temperature distribution looks like a sine wave, and it decays over time exponentially, then the solution can be thought of as that spatial sine wave multiplied by a time decaying function, that is the exponential function of time. This is the initial condition, and it fades away as the rod gets colder. But there are still constants we need to determine, and these depend on the conditions of the problem. The length of the rod, the temperature at the ends, and the frequency of the initial sine wave, and so on. These are called the initial conditions and the boundary conditions, which are a bunch of stuff that we already know about the physical problem. So now the partial differential equation describes the nature of the phenomena itself, while the analytical solution gives us the exact mathematical model for a specific physical setup. Although, for simple systems like this rod, we can solve it beautifully, as you saw. But because most systems are not simple rods, this is exactly where this approach fails. Even today, some of the most important equations in physics remain mathematically unsolved. For example, one of the clay mathematical millennium problems, which are 7 famous unsolved mathematical problems announced in the 2000 by the Clay Mathematical Institutes, each carrying a $1 million prize for whoever solves them, is related to the Navier-Stokes equation that describes fluid flow in most computational models used today. Because most systems cannot be idealized as simple rods, and real geometries are complicated, and many of the constants we mentioned earlier are not even constants anymore. They vary through time, material, and physical conditions. Even the assumption we made before that the variables can be separated cleanly was based on intuition and simplification. Reality is usually far more coupled and interconnected than that. So the system that looked clean and predictable slowly turns into something messy and extremely difficult to solve exactly. And suddenly, even though we still understand the governing PDE, finding an exact mathematical solution becomes almost impossible, almost like searching for a needle in an infinitely large haystack. Historically, this became one of the biggest turning points in applied mathematics and engineering. Partial differential equations started becoming formalized during the 18th and 19th century through the work of mathematicians such as Fourier, Euler, and others studying heat transfer, waves, elasticity, and fluid flow. Fourier introduced the heat equation in 1822, and for a nearly century afterwards, scientists could mostly solve only highly idealized systems with simple geometries and boundary conditions. But especially during the rise of aerospace and structural engineering in the 20th century, engineers urgently needed practical methods for analyzing real systems that were far too complicated for classical exact solutions like the one we talked about. And this is one of the reasons the finite element was born. Some of the early foundations appeared in the work of Richard Courant, who further developed ideas that had already begun spreading, like variational methods and approximation approaches, exploring how continuous domains could be divided into smaller mathematical regions. Later, researchers like Ray, John, and Olgierd, as the pioneers that developed finite element analysis, helped transform these mathematical ideas into practical engineering tools that we're now using today. The core idea of the solution for this problem now is surprisingly intuitive. If reality is too complicated to solve all at once, maybe we can divide it into smaller pieces, solve each piece approximately, and then combine the results together. And this is where the distinction between analytical and numerical methods truly begin. An analytical method tries to derive an exact close mathematical expression for the entire system, like the approach we used before. A numerical method takes a different approach. Instead of solving the system exactly, we discretize the geometry into smaller regions and compute an approximate solution. This eventually becomes the foundation of modern simulation tools used throughout engineering and science. I want to pause here and show you this simulation from a famous software called COMSOL multiphysics. I bet you don't know what this part is, or why we're performing a heat analysis on it. If you know, write your answer in the comments. What you're looking at is not an exact mathematical solution, it is a numerical approximation. Although I have to note, so you don't get carried away in the numerical world, one of the most important skills as a simulation specialist is knowing when you actually need a large numerical simulation, and when you can simplify the problem enough to understand it analytically. For example, in one research project I worked on last year, I needed to build a numerical model for this valve. Originally, I thought I had to build a full 3D fluid simulation of the valve, or computational fluid dynamics. A beginner version of me could have immediately jumped into constructing the entire geometry and running an extensive numerical simulation. But after understanding the physics more deeply, I realized that the system was actually axiometric, which means I could reduce the problem from a full 3D simulation into a much simpler 2D axiometric model and then revolve the results around the axis. And then I simplified it even further. I focused only on the region where the geometry was actually changing significantly, and eventually I managed to derive a much simpler analytical approach for the behavior I cared about. The point is, the deeper you understand the phenomena itself, the more you can simplify the mathematics describing it. Sometimes a very complicated numerical problem is hiding a much simpler physical insight underneath. If you're interested in other approaches researchers use to solve complex problems, you can see this video. And eventually, the idea of approximation escaped engineering. Approximation becomes one of the humanity's primary ways of understanding reality. Weather predictions, aircraft design, climate modeling, astrophysics, and fluid dynamics all quietly rely on numerical approximations. And what is fascinating is that most people imagine modern technology as exact, but it's not. Almost everything around us works because the approximation is good enough. An aircraft does not fly because we solved reality perfectly. It flies because the numerical error remains stable enough for the predictions to become useful. And weather forecast works because the simulation captured enough of reality to make reasonable predictions. And even modern artificial intelligence follow a similar philosophy. AI models do not derive exact equations, and instead they learn patterns from observations and approximate the underlying structural statistically. But perhaps numerical methods are not even moving away from nature. Because when we look deeply into the universe, reality itself already appears discretized. Matter is made with atoms, and energy is actually quantized. So perhaps the universe was never perfectly continuous to begin with. And this leads to a fascinating philosophical question. Maybe approximation is not simply a compromise. Maybe it is the only way any intelligent system can interact with a sufficiently complex reality. Also, when you look at equations, there are some constants in them that actually depends on experimental data, like the elasticity modulus that you take from stress-strain experiments, and that data is approximated, because it's done with repeated tests, and then you take the average with the error percentage. We do not fully know, but it is fascinating that our computational approximations may actually resemble reality more closely than we realize. To end what we said in this video, a famous quote from George Box that captures the idea beautifully. He said, "All models are wrong, but some are useful." And maybe that is the real story behind simulation. Not that humanity solved reality perfectly, but that we learned how to model it well enough to move forward. If you like this video, don't forget to subscribe and leave your thoughts and ideas below in the comments. Thank you for watching.